The fourth lecture on electrostatics in dielectrics. Today we shall discuss the boundary condition of the field vector. That is, what do we mean by boundary condition? Consider a surface separating two media, media 1 and media 2. All quantities in media 1 is denoted by a suffix 1. So the electric field in medium 1 is E1. Its permittivity is epsilon 1, and so like this. And there is another medium 2. There are two dielectric medium. By boundary condition we mean what is the relation between the components of the field vectors as we cross the boundary or interface separating two media. This is what do we mean by boundary condition. What are the guiding equation for boundary condition? If we confine ourselves to the electrostatic case, then it is a conservative force field, so curl E is 0. In the integral form it becomes E dot dl, the contour integral over any closed surface is 0. This is one equation, and another equation is the Gauss's theorem in electrostatics. This is called those, and this can be converted into first volume integral from volume integral, and then we convert the volume integral on the left hand side into surface integral. We get it. There's these are the two guiding equations. So first use this equation. Let us consider this is the interface. AB is the interface. This may be a curved one, the interface, but a small portion of this interface is considered, which appears to be a plane. And we consider a Gaussian pillbox which extends a part in the medium 1, another part in medium 2. So this Gaussian pillbox is a closed surface comprising of surfaces S1, S2 and the curved surface. These three comprises the Gaussian pillbox. The unit vector in this direction is n1 cap, and the unit vector in this medium 2 is n2 cap. Let us consider the vector d1 in medium 1. So this is d1 and this is d2. D2 in medium 2. The angle that it makes with this is theta 1 and this is theta 2. So if we apply this, the left hand side is the closed integral s d dot ds, now reads as integration d dot ds over s1 plus d dot ds over surface s2 plus d dot ds over the curved surface. As we are interested only on the properties of the field vector just on the either side of the interface, we make the height of this pillbox vanishingly small, so h tends to 0. So when h tends to 0, the curved surface area of the cylinder, if surface area is radius is r, so it is 2 pi rh. The curved surface area is 2 pi rh. Since h tends to 0, this curved surface area goes to 0 when h tends to 0. And if the d vector is finite, the contribution coming from this is 0. So this there can be neglected. Now the two contribution. The left hand side, in this case, the left hand side, it is d1 and we consider the area to be delta S, and this area is small, so that we can consider the field to be uniform all over this cross sectional area. So we write it as d1 dot n1 cap times delta S. This is the contribution of this, and this is now you note that d1 and n1 and n2 are directed oppositely, so we can write it as here we have used n is equal to n1 cap is equal to n2 cap. So in other words, this is the normal component of this is the d1n minus d2n times delta S. So we define the normal component dn is equal to the vector d multiplied by n cap. Now come to this right hand side. The volume element, when h tends to 0, this volume element basically goes to the surface element. In the limit h tends to 0, this is the surface density of charge, free charge times delta S. So this becomes simply a thin layer, and the surface, if sigma is the charge per unit area, then this. So we write that d1n minus d2n is equal to sigma f. This is the boundary condition relating the normal components of the electric displacement across a boundary. If there is no free charge, note that it is the surface density of free charge. When there is no free charge, surface density of free charge, d1n is equal to d2n, that is, they are continuous. And we have earlier we have found that in calculating the electric field involving conductors, we found that the electric there were discontinuities at the electric field at the interface where the charges are accumulated. This is the reason for these discontinuities in the field. Now come to the second equation, that is the curl equation. We apply the curl equation again on a rectangular contour crossing an interface. This is a portion of the interface, and we consider a rectangular contour A, B, C, D separating two media, and the contour is evaluated in the anti-clockwise sense, as the positive sense of the circulation. Now if we write this one, E dot dr closed contour, we write the closed contour is A, B, C, D, A. So this is E dot dr over AB, BC, CD plus DA. We make the breadth of this rectangle B tends to 0. If B goes to 0, this part BC, this part goes to 0 as E is finite, and this goes to 0. And this length is L, AB is L. So if this contour is an elementary contour, so the field remains almost constant over this. So we write E1 dot T1 times L. This is the unit vector in the tangent vector is T1, and the unit vector in this is T2. And similarly, this is plus E2 dot T2 times L. Now since T1 T2 are oppositely directed, we write it E1T minus E2T times L, where the tangential component ET is defined as, since the right hand side is 0, we conclude that E1T is equal to E2T. The continuity of the tangential component of electric field, electrostatic field across the boundary. These are the boundary conditions which will be found to be very helpful in evaluating many problems. Now I come to the second part, the field within a dielectric medium. Earlier we have calculated the field at an external point due to a polarized medium. Here we come to the other problem, that is, what is the field within a dielectric medium? If we consider a dielectric medium, it is composed of atoms and molecules. The field within an atom varies rapidly in space. Say it is a nucleus. If the electron is on this side, the field, it will experience a force in this direction, and on the other side the force will be on this direction. So the direction of the field changes rapidly on crossing the nucleus side. Furthermore, the electron moves around the nucleus very fast. So the field will also have a temporal dependence. So to say the electric field, the microscopic electric field is very much dependent on space and time. So what to do? By field within an electric dielectric, we mean the macroscopic field. The macroscopic field is an average over the microscopic field, and the averaging is done with respect to macroscopic space scale and also on time scale. Now, how to find out the field experimentally? If we want to find out the field, we are to place a point charge, a small point charge delta Q at the point, and what is the force that is acting on this, and in the limit the delta F delta Q with Q tends to 0 is the electrostatic field within the material. But to place the test charge over there, firstly the test charge must be small enough so that it cannot disturb the existing field or the charge distribution. So it should be small enough, and it should be placed somewhere within the dielectric. So what to do? We should scoop out a portion of the dielectric. We scoop out a portion of the dielectric, thereby we create a cavity. The cavity size is small enough in comparison with the dielectric as a whole. So it can be treated as a small cavity. At the same time, this cavity is large enough so as to accommodate a good number of molecules, so that whenever we are placing the test charge over there, we mean that it is far from the dielectric. This is the concept of finding the electric field within a dielectric. So we scoop out a cavity and place a test charge and find out what is the field within the cavity. It is found that the field within the dielectric depends on the shape of the cavity digged out. Let me consider a dielectric. The field within the dielectric is this ED. It is directed in this direction. We scoop out a needle-shaped cavity. This is called a needle-shaped cavity. the polarization charge will appear. The polarization charge will appear, positive charge and negative charge will appear in this. Our interest is to find out the field at this point C at the center of the needle. See, the needle is chosen in such a way that its length is much larger comparison to the radius or dimension of this cross-sectional area. So the total polarization charge that will be produced on these two circular faces will be proportional to the area of the circular faces. So this is P dot n times delta S, and since delta S is small, this is nearly zero, the total charge is very small. The total charge that appears on the two faces are very small. Furthermore, the point under consideration is far away from this. So the polarized charge will have very little effect on the field over there. So if we call the field within the cavity C, this cavity field is equal to the field in the dielectric, and the field is directed in this direction, and polarization is also in this direction. So if we dig out a cavity, needle shape cavity whose axis is parallel to the polarization vector, then the field within the cavity, needle shape cavity, is equal to the field within the dielectric. This same result can also be arrived at if we use the boundary condition. We choose a rectangular contour shown in the red line, and it is traced out in this. So this part is small, so we replace this, and the field within the dielectric is ED, and the field within the cavity is EC. So by using the continuity of the tangential component, we find that EDT is equal to ECT. The tangential component is continuous. Since the field is in this direction, there is no transverse component, so we conclude that they are the field as well, which we obtained there. Now we change to the cavity in the shape of a disc shaped cavity. Within the dielectric medium, we consider a disc shaped cavity. The cavity is in the form of a circular disc. Here, this area are the appreciable, and this is the direction of polarization. Again, our problem is to find out the field here. The polarization, positive charge will appear there, and the negative charges will appear there. Here, we find that the polarization charge is indeed important. And because the surface area are large enough and the point under consideration is not far away from the surfaces, so the polarization charge will indeed contribute something. So the polarization field is equal to sigma p by epsilon, and sigma p is given by p dot n cap upon epsilon 0. Because here it is the vacuum, so epsilon 0. In the vector form, it is. So the field within a disc shaped cavity, EC, is the field within the dielectric plus field due to the polarization, and this is we note that this is we can multiply this epsilon 0 EC is equal to epsilon 0 ED plus P. So this is the displacement vector in the cavity, and this is the displacement vector within the dielectric. This is the relation. The same thing we can arrive at by using the continuity condition of the normal component of the D vector across the surface. uh, in that case we are to consider a pillbox over here, and we are to apply the law. And since there is no free charge, sigma f is 0, so ddn is equal to dcn, and since the field has only normal component, this is valid also in the vector form, and this is the relation. Lastly, the most important one is the spherical subcavity. A cavity is digged out in the form of a sphere, and our aim is to find out the field at the center. This is a spherical subcavity, and we assume that it is, as before, we assume that it is placed in a uniform field polarization, where the polarization is uniform, and I will perform this calculation in detail. So the field, what I am going to calculate is the EP at the center of a sphere placed in a uniform polarized, placed within uniformly polarized dielectric, placed in uniformly polarized dielectric. This is the case. We assume, let me situate, this is the sphere. We assume that the polarization is along z-axis. So assuming polarization to be along z-axis and it is uniform polarization, so it is k cap p, where p is a constant. This is the polarization part. Now, if we consider a surface area over there, the surface area is ds prime, which is, if A is the radius of the sphere, if A be the radius of the sphere, the surface area is a square sine theta prime d theta prime d phi prime. This is the area. So the surface density of charge sigma p at r prime, the source coordinate, is p times n prime. So n prime is directed in this direction. This is the n prime, because this cavity has been scooped out, so the outward normal is this. If we write in terms of r cap, this will be minus p dot minus r cap, because the r cap is directed in this direction. So, and we know that r cap, what is r cap? R cap is I cap sine theta prime cos phi prime plus j cap sine theta prime sine phi prime plus k cap cos theta prime. If we cross it with p, then only this part survives, and this is minus p cos theta prime. So what is the charge? This part will again require, what is the charge? Charge within ds. Charge on ds prime, this is dq, is equal to sigma p times ds prime, and sigma p is minus p cos theta prime. This is sigma p, and this is a square sine theta prime d theta prime d phi prime. This is the total charge. What is the field? The field due to this is directed along this, so this is directed along a minus. So the corresponding field charge dq by distance. Distance is a square and the direction is along minus r cap. Note this. This is the charge on the surface area ds prime. The distance is this. Since it is placed in vacuum, so it is 1 upon 4 pi epsilon 0, and the direction is in this direction, which is against the r cap, so there is a minus sign. Let me write here one r square will come, that will neglect this r square term, so the result is 1 upon 4 pi epsilon, and from this part we will have minus p. This is cos theta prime sin theta prime d theta prime d phi prime. And from r prime cap, this will appear with a negative sign. So this sign will become positive, and we will have I cap sin theta prime cos phi prime plus j cap sin theta prime sin phi prime plus k cap cos theta prime. And to get the total field, we have to perform integration over d phi prime in the range 0 to 2 pi and d theta prime in the range 0 to pi. If we perform integration over phi over complete cycle, this gives you 0, this gives you 0. So the only this part survives, and this part is independent of phi, so the phi integration will give you a 2 pi factor. So the total field, if we calculate total field at the center EP, this part will be there, P upon 4 pi epsilon naught. 2 pi factor will come from this integration, and the field is along k cap. Field is along k cap, and then the angular part cos theta, there is on the cos square theta. So integration involves cos square theta prime sin theta prime d theta prime from 0 to pi. We introduce u is equal to cos theta prime, so that du is equal to minus sin theta prime d theta prime. When theta prime is 0, u is 1, and when it is pi, it is minus 1. So we can write it in terms of u. These 2 pi cancels, k cap p by 2 epsilon naught, this cancellation, and this is minus 1 to plus 1 u square du. Note the change. This is u square, this part is minus du, and the limit is plus 1 to minus 1, which we have changed. So result is 2 by 3. So p, this we couple to vector p upon 2 pi 2 epsilon, and the integration result is 2 by 3. So it is p by 3 epsilon naught. So the field within the cavity, is C in this case, is ED plus P by 3 epsilon naught. This relation has very important, this calculation has very important relation in connection with the evaluation of field within dielectric liquids, and it leads to an important relation known as Clausius-Mossetti relation. Only one small thing left in connection with dielectric. Let me cover up also this thing, the constitutive relation or the introduction of susceptibility. we have till now I haven't introduced the concept of electric susceptibility. To conclude my discussion on electrostatics in dielectric, I shall take up the case of the polarization vector. The polarization vector is in general depends on the electric field. So polarization is a function of electric field. Writing in component form, so pi, where I may 1 I is equal to 1 is px, j 2 is py, 3 is pz, is a function of ex, ey, ez. In other words, we write it in a compact form as we perform a Taylor series expansion of P in with the zero field case. So we write Pi with E means vector E is equal to Pi at 0 plus this term. Let me first write the term. The term will be del Pi del Ej multiplied by Ej, because we have expanded it in terms of zero field case, and J may be 1, 2, 3. So there is a sum over J from 1 to 3. Similarly, the higher order terms will come. The higher order terms are like this. J and K, and this will be but there are some factor will also appear. Some factor is missing. The factor is that when we have J and K are same, the term will come with 1, weightage 1, and when J and K are different, it will come with a factor 2, because there will be a term like del Ex in the denominator, del Ey, another term will be del Ey, del Ex, which are same, so there will be a factor of 2, which we could easily taken care of as by writing the factor as 2 minus delta jk. It is a factor. When J and K are same, this is 2 minus 1 is 1. When J and K are different, it is 2. So this is the factor. One another way of writing it is this: Pi at 0 plus sum over J, Jk, beta I Jk, Ej Ek plus higher order terms. If we consider what is P, if we neglect ferroelectric materials, then there is no polarization in absence of electric field. So if there is no spontaneous polarization, this part is 0. For non-ferroelectric materials. So we write P for this term is dropped out. Experiments shows that if the field E is not too high, one need not to consider this part. This can be neglected. So the relation reduces to this. Oh, let me say one thing on. This has 9 components because I can run from 1, 2, 3, and for each I j can have 1, 2, 3. So in together it will have 9 components, and it is called a tensor of rank 2. And this have 27 components, it is rank 3 tensor, and the other higher order tensor will appear. So if we retain ourselves up to this and exclude ferroelectric material, this comes out to be this is known as what is known as polarizability tensor. If we write it in matrix form, then the relation becomes this. The relation becomes px, py, pz. This is alpha xx, alpha xy, alpha xz, alpha yx, alpha yy, alpha yz, alpha zx, alpha zy, alpha zz, so that px is equal to alpha xx ex plus alpha xy ey alpha xz ez, which is nothing but this relation. This is known as polarizability tensor. There are materials for which these cross terms are zero, only the diagonal term remains non-zero, and also they are same. If alpha ij is equal to some constant times lambda ij, it is called isotropic material. The medium is called isotropic, and in that case p vector is related to e vector, p vector is related to e vector through a lambda, constant lambda. In that case p is proportional to e and p is collinear to e. But remember, this relation holds for a very special type of material called isotropic material. And one writes it as epsilon 0 xc e, where xc is called the electric susceptibility. Electric susceptibility. So if we come to vector d, d vector is defined as epsilon 0 e plus p, and for p I write epsilon this. So if we take epsilon 0 common, this is known as absolute permittivity of the medium, and where absolute permittivity is written as epsilon 0 1 plus chi e. Chi e is a dimensionless quantity, and this can also be written as epsilon 0 epsilon r relative permittivity, or epsilon 0 k the dielectric constant. These are the same. So these are the relations amongst the three field vectors, and is known as the constitutive relation.